So my goal today now is to help expand your ability to do calculations to not just mass, but to be able to do volume, concentration, and really once you pick up these principles, you can really convert between anything. I'd like to give you just a silly example to start class. If you get the concepts of stoichiometry, you could start with something like this. If I gave you 1,000 joules of energy, and then I told you that when you burn it, there is 15 moles for every 7,000 joules. And then if I told you that this was for, let's say, methane, then if I told you that you get 2 oxygens for every 1 methane, kind of cancel this. And then if I told you that your oxygen was a molar mass of 32.00 grams per mole, can you guys kind of see how I'm able to like run a running string of numbers? And I can use almost any, let's call them like attachments available. Here I got rid of the joules attachment. Here I got rid of the moles attachment. Here I got rid of the methane attachment. By the time I'm done, I've now calculated how many grams of oxygen I would expect based on 1,000 joules. Does that make sense? And so once you get these concepts here, all you really have to know how to do is just change out whether this has to be grams always. Because so far, all I've worked with you guys on, I've got a picture somewhere here. Here it was going grams to moles, use coefficients, and go back to moles again. But that's not the only thing that we can do. You guys get where I'm going with this? So for the most part, I'm just going to show you some examples today, and that should hopefully be enough. So where were we? So I'm going to read off my slide. I rarely do this, but from a practical standpoint, when we start solve stoichiometry problems, we always want to go from quantity to quantity. But it doesn't always have to be grams, so today we're going to add on volume and moles per liter. So let's try some examples. Like really, I think that's the best way to do this. So here's what we're going to do. We're going to try to figure out how much copper you're going to need to produce 25.8 grams of gold. So ultimately, my goal here is I'm going to try to produce some gold. The question is, how much copper should you bring? And it's going to give me a little more information. It's going to tell me the recipe. It says we're going to react solid copper with gold 1 nitrate. So, thoughts? What's the first thing we probably need in order to proceed? Yeah, we need a balanced chemical equation. If we don't have a recipe to go off of, we're kind of stumped. So, if I were to take solid copper, and if I were to react it with gold 1 nitrate, that looks like this. Gold 1 nitrate, why don't I go with aqueous? I'm not actually sure whether it's solid or not, so I'm just going to take a stab at it being aqueous. What kind of reaction is this? Single replacement, which means that we need the copper to go with the nitrate, and we would also get solid gold. Now, some of you have actually already come across this particular twist before. Which copper should we use, though? Yeah, if it doesn't tell you, go with the most common one, which I believe is copper 2. Is that right? However, you actually have an assignment question where if I give you the breakdown and I tell you that copper 1 is like, say, 55% and copper 2 is 45%, then you could actually solve it by knowing like what the breakdown is. But if I don't actually tell you that, then just go with the most common one. So copper 2 nitrate was most common. So let's do that. Because I don't actually know what the percentage of copper 1 to copper 2 happens to be. I'm sure we could Google it. Okay, well, this one right here, we're actually still just working with masses. So I actually haven't added anything new to this question. So start with 25.8 grams of gold. Oh, good catch. Thank you. 2 and 2. Sometimes I forget to balance, and I balance when I get to this step right here. We need to do a mole for every, I think it's 197. 87? Oh, that's not it. What is it? 196.97. Thank you. 196.97. Okay, so that cancels out the grams. Then we need to get rid of gold and turn it into copper. Now I need to have my ratio. So the relationship is for every 1 copper, I get 2 golds. And then since it's asking for how much copper we need, Then we use copper's molar mass at the end. Hopefully this is not, hopefully you're getting better at this. No, it's very repetitive over time. Then all we need is a calculator. Gold will cancel, moles will cancel. All right, 25.8 divided by 196.97 divided by 2 times 63.55. I got 4.162. Okay, and then make sure you're careful on sig digs. Based on that, then you need 4.16, I guess, grams of copper. If you bring that much grams of copper, then that's exactly how much gold you'll produce when you're done. Any issues with that one? That one's not actually new. I'm not getting any. Okay, we're moving on then. Okay, well, what I want to do now is let's try to not just always. I found this picture online. Let's not always go from grams to moles to moles to grams. What we could do is we could throw in things like liters. And we've actually learned a liters number from our previous unit. Do you guys remember this ratio? Do you guys remember these ratios right here from our previous unit? It wasn't that long ago we did it. At STP, we learned that there was 22.4 liters in a mole, or at SATP, it was 24.8 liters in a mole. Now, in theory, we can actually find those for other calculations. Like, let's say it's not at STP or SATP. Let's say that I told you, randomly, just kind of off to the side, let's say I told you that it was 200 kilopascals and 15 degrees Celsius. We could actually still calculate that same ratio using PV equals NERT. Let me show you how. So I'll just write this out. Suppose it was this. So then you'd write out, say, PV equals nRT. And what we're looking for is a liters to mole ratio. So you really need to divide by N on both sides and divide by P on both sides, leaving you with volume over moles. And then you'd have R, T, and P. Now, it's 22.4 at STP. It's 24.8 at SATP. This is neither of those two conditions, but I can still find my numerical value. I just got to take 8.31 times by, what's that, 288 Kelvin, and divide by 200 kilopascals, and that will get me my liters per mole number that I may want to use. Do you guys get what I'm saying here? So most of the time when we're working with volumes, it's either going to be 22.4 or 24.8. But if I give you other conditions, we can still calculate a liters per mole number, because really that's what V over N is going to be. And so what we're going to do is we're going to have a different attachment. When we use our stoichiometry equation, rather than going grams to moles, we might go liters to moles. Let's try an example. Question. Hydrogen gas is produced when you react sodium metal with water. How much sodium is required to produce 15.6 liters of hydrogen? So the twist here is that rather than me giving you a grams number, I'm starting off by giving you a liters number. Okay. I mean, the same basic principles apply. You just need to make one slight little twist. So first thing though you should do is write your equation. We're going to take sodium metal and add it to water. If you're going to make hydrogen gas, what's the other byproduct? No. This one catches kids all the time. What is water made of? We've actually learned this in our first unit. H and OH. When you undergo a single replacement reaction and kick out the hydrogens, the sodium goes with OH. So it actually makes sodium hydroxide. It's a really common mistake that people think that it should be say Na2O, but that's not correct, because that's not how a single replacement reaction would work. The H gets kicked out and becomes H2 gas, and then the OH is what joins up with the sodium. So there's our balanced equation. Actually, it's not balanced, is it? to balance it, we'd need to go with, let's see, a 2 here, a 2 here, and a 2 here, I think. Yeah, I'll do that. One of the things you guys are going to notice about doing these equations is that there's a lot of places where you can make mistakes, and any mistake along the way screws the whole thing up. If you mess up a molar mass, you're done. If you write an improperly balanced equation, you're done. You know what I'm saying here? Like, there's so many little steps along the way that if you'd have written the equation wrong, you know, so. Okay, so here's where I'm going to start then. I'm going to start with this value here that I was given, 15.6 liters of hydrogen. Now, normally we want to use a molar mass, but in this example here, I don't have a molar mass. I want to get rid of liters, so I need some sort of ratio that gets me into moles, but gets me out of liters. But the good news is I know that value at SATP. At SATP, there are 24.8 liters in 1 mole. All I'm doing is, rather than starting with molar mass calculations, I'm starting with a volume calculation. That's all. I will not proceed like usual. What's the next step we usually have in one of these things? A ratio, yep. Yeah, so let's get rid of hydrogen and solve for sodium. And again, the whole thing gets buggered up if you don't have the right balanced equation. So you need 2 sodiums for 1 hydrogen. Just make sure 2 sodiums, 4, 2, 2. Yeah, we're good. Okay, and then for the last step, it said what mass is required. So although the first attachments I used were liters, when I'm finishing this off, I want to use grams again still. So then use like a molar mass. Sodium, I believe, is 22.99. And then this mole cancels that mole. This hydrogen cancels this hydrogen. And when I'm done, the only units that I haven't canceled are the grams of sodium. So I just need to know. Put it all together. With SIGDIGs, I got 28.9. Let me know whether you guys get the same thing. Can you guys see how this is literally the same thing that we're doing with mass, only rather than using grams and grams per mole, I'm using liters and liters per mole. But like it's the same kind of concept there. Once you get the idea, you can make a string that goes for forever. Like a silly example, there are 12 donuts. I'll start with this actually. I have 7 donuts, and I happen to know that in 1 dozen, there are 12 donuts, and then the price happens to be $5.99 per dozen, and I happen to know that I make $15 in an hour. I mean, I'm just making a really silly example here. But like, now I've managed to figure out if I want to buy 7 donuts, now I know how many hours I need to work for. That makes sense? I mean, this is a silly example, but like the basic principles apply, as long as you can kind of see how things cancel. Any questions on this? No, let's try another one. This one I threw a little bit of a twist in. I've already described to you how to solve it. You might notice as you look at some of the numbers there, I gave you a pressure and a temperature that are not SATP or STP. We're going to have to, before we move on, we're going to have to calculate the molar volume under those conditions. So, I mean, I can do that first if I'd like. You guys get what I'm saying here? These numbers right here are not STP or SATP. So I'll take PV equals inert. I will rearrange it to volume over moles equals RT over P. It'll be 8.31. Let's see, add 273 to it. That's going to be 363. So I have a molar volume that I calculated of 7.08 liters per mole. Anybody else get that? Why is it so much lower than SATP? Say that louder. Yeah, the temperature is one factor. The pressure is the other one. What happens when you increase the temperature? What happens when you increase the temperature? According to Charles' law, if you increase the temperature, it also increases the volume. Yeah, now, but it's almost like it's a backwards relationship here, though. It means, though, that you'd actually need less volume then for your mole. How do I describe this properly, though? Hmm. Maybe that train of thought I can't follow up on. Because Charles' law almost makes it seem like you should have more volume, but it's the opposite. I'm just trying to figure out how to describe that. Anyways, I'll leave that. Are you guys okay with calculating that value at least, though? Anybody want to grab breakfast? I'll pause for a second. How do I explain that? Oh, you know what? I think I can explain it better. Although the temperature would want you to have more volume, what happens when you increase pressure, though? If you up the pressure, it decreases the volume. So it's actually not the temperature that's the main driver of this one here. It's the pressure. Your pressure is so high that when you up pressure, according to Boyle's law, volume has to decrease. Does that make sense? So it's mostly because of this number right here that this value is so low. I think that's the explanation I should give. Anyways, the other thing we're going to need though is a balanced equation. So we're going to react hydrogen gas and nitrogen gas to make ammonia. By balancing it, you need that. I believe now I finally have everything I need to proceed. So I need to have a balanced equation. And because this isn't under SATP or STP conditions, I need to know how much volume per mole we're going to have. It's lower because that pressure is so high. Whatever should I start with? Say louder. Yeah, you should almost always be starting with a single value. Never start with a ratio. 7.5 kilograms is a good place to start. But if it's okay with you guys, I'm going to make it 7,500 grams. Can you guys just times by 1,000 in your heads? Wait, I don't want mass. That was of hydrogen, by the way. So since that's the hydrogen mass, I need to get rid of grams. So I need to know hydrogen's molar mass. 2.02. Don't forget to double it because it's diatomic. So that cancels out grams. Then we no longer want to know about hydrogen. We want to know about, what is it, ammonia we need? Yeah, we want the volume of ammonia. And then for relationships, it's 2 of these for every 3 of these. And then for the last step, it doesn't actually want mass of ammonia, it wants volume of ammonia. But fortunately, we just found that number just a second ago. It's 7.08 liters per mole. Now, when I use that 7.08 number, though, you use the exact value, right? Don't use the rounded number. So in theory, then, this will cancel with this one with this one. And the only thing that I'm left with is how many liters of ammonia is left. So 7,500 divided by 202 times by 2 divided by 3, and then times by that 7.08 number we just found. I got this. 17527. No, just need to clean it up a little bit here. 2 most common ways of fixing this. We need 2 sig digs, it looks like, based on this guy only having 2 sig digs. So you could call it 18 kiloliters. Everybody get how I pulled that one off? Make it a kiloliter by moving the decimal place back 3 times here, and then it rounds up to 18. Or you can make it a 1.8 times 10 to the 4 liters. Either of those would be valid. That makes sense. All right, I want 2 more examples. 2 more examples. We can also do the same sort of thing, but rather than using liters per mole as though it's like a volume of a gas, We can also use moles per liter as though it's a concentration. I want to make sure that I'm clear about this here. We can use moles per liter as a concentration, or we can use liters per mole as the volume of a gas. And like they both work relatively the same. It's just depending on which sort of information you have. So I'm going to do some stuff right now that involves solutions where I'm going to give you concentrations in moles per liter. The same sort of thing still apply though. Like we're still going to try to cancel out our units. So on this particular one right here, we're going to take ammonia and phosphoric acid, and we're going to produce ammonium hydrogen phosphate. The hardest part to this one right here might be actually getting the equation. What's ammonia? Okay, what's phosphoric acid? It's H3PO4. It's actually this one that's listed right here. Phosphoric acid is H3PO4. And then it says we're going to produce ammonium hydrogen phosphate. Ammonium is an NH4. Does anybody know what a hydrogen phosphate is? Yeah, it's HPO4. Now, HPO4, though, I believe has a -2 charge on it. Is that right? HPO4? Which means that if this guy has a +1 charge and this one has a -2 charge on it, you're going to need to put 2 of those there to make it work. Now, I hope this one works out properly. Because if I remember correctly, in order to balance, the only thing we need to do now is put a 2 here, and I hope that solves it. If I put a 2 here, you're going to have 2 nitrogens. To the 2 nitrogens you have here, you're going to have 6 hydrogens plus 3 more is 9. And then in this molecule right here, you have 8 plus 1 more is 9. And then like PO4 right here, you have an entire PO4 right there. So this is going to be one of the things that's going to start to become more tricky, is that you're not always going to be given simple equations to work with. We're going to start making that a little bit more challenging. Right? So you probably haven't seen an equation like this before, but hopefully you have the skills to be able to like problem solve and troubleshoot how to make this new equation here. You know what I'm saying there? Really, the only thing we needed from this, though, is the ratio. We need to know that for every 2 ammonias, you get 1 of each of these guys. That's the real whole point of this part. Okay, so then for the last thing, we got to figure out how to set up our ratios. So I always recommend start with the one value you're given that's not a ratio. This guy right here is a ratio. Don't start with that one. This one right here is also a ratio. Don't start with that one either. The one you should start with then is the 1.00 kiloliters. Start with that one. So that's actually 1,000 liters of H3PO4. All right, next up. Do we want liters? No. What do we need to get into in terms of units? Moles, actually. We have to get to moles first, and then we'll get to volume. So in order to get into moles, I'm going to need some sort of ratio that gives me moles over liters so that those liters can cancel. Do we have such a number that gives us that? Yeah, the 12.9 moles per liter can go right there. I have such a number. So I've now used this one and I've used this one. Now that I've converted into moles, now I can get rid of the H3PO4. And what am I looking for? What volume of ammonia? Okay, so I want ammonia on top. And then this is the whole reason why you have to be able to write your balanced chemical equation, is all of this bit right here was just so that I knew to put a 2-to-1 ratio here. If you misbalance your equation, the whole thing's buggered. What do I want to solve for? What's ultimately our goal? Okay, so ultimately our goal is volume, but to get there, though, I had to go through moles. Okay. So ultimately I want to get to volume, which means I want liters on top, and the remaining unit I have left here is moles. Which means I need to know a liters per mole value for ammonia. Well, I don't have a liters per mole value, but I sure have a moles per liter value. I can still use this number, except I have to make sure I put it in the right location. The 14.8 number has to go right here because there's 14.8 moles in 1 liter. I've flipped that fraction upside down, but it'll still work. It just means that I'm writing it as its like reciprocal format. Right? And if you can visualize this now, the liters cancel with this liters to get us moles. H3PO4 canceled here to get us ammonia. We don't actually want moles, so we're going to cancel those moles there. And now that I'm done, the units left are liters of ammonia. Let me know if you don't get that one. You guys get that value? I want to show you a nifty little trick. You know how it started as 1.00 kiloliters? By the time I'm done here, this probably also could be written as a kiloliters number. Like when I'm finally done with sig digs, you could call this 1.74 kiloliters of NH3. Here's a nifty little trick that you could do if you'd like to, if this makes sense to you. You know how way back here, I converted my 1 kiloliter to 1,000 liters? Let's say that you didn't do that. Let's say that you left it as 1.00 kiloliters. You can actually still do that, but what's going to happen here is that only the liters will cancel, and only this liters will cancel right here, but you're still going to have a kilo prefix just kind of sitting there. If you did the exact same math now and did 1 times 12.9 times 2 divided by 14.8, you would end up getting 1.47, but then it wouldn't be liters of NH3, it would be kilo liters of NH3. So if you want to, you can actually like not remove like any prefixes here, like kilo or milli or centa. Leave them there, and it just means that your final answer will also be in kilo or milli or centa. It depends on whether or not you feel it's necessary or not. Make sense? All right, last one, then we'll call it a day. Let's calculate the concentration of sulfuric acid required to neutralize 0.150 moles of potassium hydroxide if I give you 100 mils of acid and 15.9 milliliters of base. Okay, so first step, we need to write ourselves a balanced equation. We're going to need that at some point. What's sulfuric acid's formula? Yeah, H2SO4. Okay, and then we're going to neutralize potassium hydroxide. That'll be KOH. We'll go with aqueous for these guys. What kind of reaction is this? You could either call it neutralization or double replacement. They're both kind of the same thing. What ends up happening is your K will go with your SO4 and make it K2SO4. And then your H will go with your OH. H and OH together makes water. Yeah, H2O water. I'll say that's probably aqueous. So all this work I'm doing right here is solely for the purpose of getting a ratio. I need 2 of those. 2 waters. That's it then. Wait, now I threw this one as my last one here because sometimes kids will get stumped and go, okay, well, which number should I start with? I can tell you which number you shouldn't start with. Don't start with this one right here. Don't start with your ratio. Okay? Because you use your ratios to cancel out units. But then the issue is, should I start with the 100 milliliters of acid or the 15.9 milliliters of base? It actually does make a difference. The correct answer is start with the base. And I'll show you why as we start going. So I'm going to start with the 15.9 milliliters of base. If it's okay with you, though, I'm actually going to leave it as milliliters, though. I'm going to use that little trick I showed you. I'm going to go 15.9 milliliters. What is our base? Which one of these things in here is the base? Yeah, the KOH, the potassium hydroxide. Okay, now I know there's a milli unit just sitting in front of here, but really I need to get rid of liters. So in a way I need to find some sort of ratio that gets rid of liters and gets me into moles. We always want to get to moles. That's kind of like our transitionary piece. So I can cancel just this liters right here with that liters there. Now here's my question. Do I have a moles per liter value for potassium hydroxide? Yeah, that's the 150 moles per liter. Okay, let me explain why you shouldn't have started with the acid. If you attempted to start with the 100 milliliters of acid, so don't write this out here, you would then need a moles per liter number for H2SO4, and we don't possess that number. You know what I'm saying here? So because I don't possess this number right here, starting with that one doesn't really make sense. But because I have a liters and a moles per liter number for the KOH, that one makes sense to start with. Okay, what I've gotten to now is I've gotten my liters to cancel, but I still have a milli sitting out front. That's fine. The next step is I no longer want to work with KOH. I want it to actually be, what am I looking for? Concentration of sulfuric acid. So I need H2SO4 on the top of the fraction with my 1 to 2 relationship there. Okay, so that gets rid of my KOH. Okay, what is my goal? Ultimately, I'm looking for, what is the typical unit of concentration? Moles per liter, yeah. Now, what am I currently at? Moles, right? Right now I have moles of H2SO4, but I want it to be moles per liter. Now, people show this in lots of different ways. My personal preference is to write it like this. I write 1 divided by 100 milliliters. So that's kind of squishy in there. The reason why I write it like this is that what we really need to do is we need to take this moles right here, and we have to divide it by liters. Only I'm going to keep it in milliliters. The reason why I'm going to keep it in milliliters, I still have this milli over here. This milli right here will cancel just that milli sitting right there. And when I'm done, I will have moles per liters. This is a weird little trick here. What I'm literally doing is writing a reciprocal. Almost all of you guys have talked about a reciprocal at some point, right? Because we've done that in our math class. I'll chat with you more later if you want. But like literally all I'm doing is rather than writing it as 100 milliliters, I'm writing it as 1 over 100 milliliters instead. I'm doing it like that. And when I write it as 1 over 100 milliliters, then the milli cancels, this cancel there, this cancel there. What we're left with now is moles per liter of H2SO4. So math-wise, take 15.9 times by 0.150, divide by 2, and also divide by 100. You guys know how like this 1 over 2 right here? You don't really need to times by 1, right? You can just divide by 2. Same logic right here. Rather than timesing by 1, just straight up just divide by 100. I got this. 0.011925. So finish it off, we need 1.19 times 10 to the minus 2 moles per liter of H2SO4. That's the concentration required to neutralize. Today I try to show you guys a few little tricks I've picked up along the way to help keep it organized. You don't have to write it in the same way that I do here, but I find that if you can start by going this times this times this times this times this, and you just start canceling off stuff, it's a really easy way to keep track. And so long as you've canceled out everything you're looking for, you're good to go. That makes sense? Now, I do have to warn you, though, there's a whole bunch of different little twists I can throw along the way. For example, maybe I won't give you grams per mole, maybe I'd give you something else like kilojoules and kilojoules per mole. But the same logic still applies. Does that make sense? Or I could, one of the things you're going to have to do is balance an equation. But I might give you a slightly more challenging equation to balance, like the one we did a few slides ago. Right? So there are some little tweaks I can give along the way to make it more challenging, but honestly, like once you get the basic concept, it's very, very repetitive. Okay, you guys have any questions of me? Okay. Wait, you should be able to do, believe it or not, you should be able to do at least the first like 4 or 5 questions on your assignment now. So I would suggest either work on that little by little. There's only like 7 questions total, I think, even. Or work on your labs, I guess, because you guys still have about half an hour left today. So tomorrow I'll do one more set of notes. Friday we'll have a work day, and then Monday we're going to try our first quiz. And we'll see how it goes. So. Yeah. Yeah, go for it. Just pull out the file folder there.